Alright, hello everyone, this is Mr. Crozier. I'm going to help you with some Chapter 1 review problems. I have the answer and key here, but I'm just going to talk about these problems, make sure you know how to do them. Alright, number 1, create a table to estimate the limit. Well, there's our value. This value always drops down and goes in the middle. And then we pick some numbers that are close to 0 on the right side and close to 0 on the left side. Take them, plug them in your calculator, and input those. The easiest thing to do is to go to the table set and start this table maybe at 0, 0. But if you put it on ask down here, you can input the values you want. So you can take these, I'm going to delete these right here, but any value you want, let's say 3.6, press enter, it will give you the output. Now I have a different function in here. So you type this function in here, then when you go to table, any input you put, your calculator will take that, run it through this, and give you the output. So that's how you go from inputs to outputs. Horizontal asymptotes. The key of our definition is that you find these two limits, and if they equal a real number, then you have a horizontal asymptote. The only other option for C would be infinity, and if it's infinity, it's not an asymptote. If it's a number, it's an asymptote, and you should be able to comprehend that on the graph. If we're going out to infinity, if it comes to a number, like let's say number 1, that's an asymptote. But if it goes up here to infinity, well, that does not exist. There is no limit there. There's no asymptote. Trig functions, factor out the 2 and the 3. Then you're left with this value here. And that is, when we memorize, that is just 0. Again, if you've forgotten it, a real easy way to do it, if you forget it, is just to graph it. Let's just graph that and see what it does at 0. There's the function. Let's see what it does at 0. I hit graph. Well, there it is. Let's figure out what we did here. I think it might be in radians would be better. Second graph. There's the function right there. It's right in there. Let's hit zoom in. Let's go down and press enter and zoom in. So where is this function going on day 0? Well, it's right there at 0, so that limit is 0. Now try the value at 0. The value at 0 is not defined, but we do have a limit. Again, make sure in mode you're in radians or degrees. Most of our work will probably be done in radians in this class, but you gotta make sure you go back and forth or you won't get the graph you're looking at. Discontinuities. The only one we're talking about, the only one we have so far, is when the denominator is 0. So what numbers make this denominator 0? Well, that does, but we're dealing with the world of real numbers. There are no real numbers. Find the limit as x goes to 0. Well, we plug in 0 here, it's undefined, so we get this 0 over 0, or something over 0. Not going to be 0 there, but something. Well, actually, it will be 0 over 0, so indeterminate form. Well, do some fancy algebra, and the fancy algebra is, let's write this twice, distribute it, simplify, comes out to be just 14h plus h squared over h. Divide that, and now you can plug it in. The values here, f of 1, on day 1, the output is 2. On day 3, the output is 0. The limit on day 2, right here, well, there is a point there. There's an infinite number of points there. If it's continuous, there's a point anywhere you want to make a point, you can make a point. And that point's at 2, 1. Going to 1 from the right side. So what I tell people to do on this problem is simply look at 1, there's day 1, and just look at the graph just from the right side. And it appears that this graph is going down to 0. I mean, it's defined up here, but it appears to be going down here. That's where it's going. So that's why it's 0. Just look at the right side. Ignore the left, do the right. On day 2, it's 1. F of 0, there is no value there. 3 from the left side. So again, cross this off. Where is this graph going? Not where is it going? Well, it's going down to 0. Limit on day 3. Left side and right side do not meet, no limit. Plug in 0 is 0. Multiply by the conjugate, everything divides out. Right here, the x's come out. Don't factor the bottom. Leave it like that. Plug it in, 1/10. Page 2, explain how to find vertical asymptotes. So there's lots of different ways, but this is the one we've done now. There are numbers that make the bottom 0 and the top's not a 0. So if you find a number where it plugs into the bottom, gives you 0, plugs into the top, doesn't give you 0, well then that's an asymptote. And the most basic one I can give you of this is the equation this, 1 over x. What numbers make the bottom 0? 0. What numbers make the top 0? Nothing. We have this case. Hit graph, and what do you see right at day 0? There's an asymptote because there's an infinite discontinuity. It goes up, it goes down, but it can't be 0, and it's not a hole that can be removed. There's no way to remove this x. So it is a vertical asymptote. Find the limit. We learned a shortcut here. If we're going to infinity, the only thing that's concerning to us is the highest power. So I really just rewrite this as the limit as x goes to infinity of a negative x over 5x squared. With polynomials, it's okay to do that. The reasoning is about significance. If we're going to infinity, x squared is much larger than the 2. And the infinity here is much larger than the 4. So this is what's significant. Now when you plug in infinity, well, you get negative infinity over 5 infinity squared, which is just another version of infinity, which means it's indeterminate, which means we do some algebra, and the algebra is divide by x. I take the lowest power. Some people take the highest power. Does not matter. I take the lowest one. You get this. Now you can plug in infinity and you get this, and then we can comprehend this. We can't really make sense of this because it's indeterminate. This makes sense. 1 over the largest number in the world is 0. Vertical asymptotes here, well, factor at first, and I have these two numbers. What numbers make the bottom 0? 3 and negative 3. If I plug in negative 3, though, watch what happens if I plug in negative 3. I have a 0 over 0, which means 0 over 0, and that's not our rule. So 0 over 0 means no asymptote. This is a hole on the graph. This is a asymptote on the graph. So that's the difference. If it can come out, it's a hole. And just always, if you can't remember that, go back to this graph right here. That can't come out. So it is a asymptote. If I were to change it and put an x there, now I graph it. I could factor that out, so watch the graph now. Now it's not an asymptote. Now it's a straight line with a hole, and still watch. Second, calculate, hit the value, 0. There's still not a value there, but there's not an asymptote there. There's a hole. If you can factor it out, it's a hole. If you can't, it's an asymptote. Any discontinuities? Well, negative 1. Plug negative 1 there. Can you remove it? No, there's no way to factor it out. I had people trying to factor it out like this, and they factored that out, but that's not factored right. That 2 times x is 2, but 2 times 1 is not 1. So the top's not factorable, the bottom's not factorable. You can't factor this out. It's not removable. It's an asymptote. And again, go to this, type it in, you'll have your calculator to check your work. And we definitely see an asymptote right there at negative 1. Let me zoom standard, see what it looks like standard. Yep, right there. And if you want to hit zoom box, hit zoom box. Let's go all the way over here left. There's my cursor, press enter. Go all the way right as far as I want to go. Drag up a box. Around this key part of the graph, press enter. I think we're going to get a good view. And there we go. And there's that line. Sometimes your calculator draws it, sometimes it doesn't. Just depends on the window. Alright, here, story problem. We have a function that's taking time and getting population. So if I plug in the current population, which is now, which would be 0 years from now, That would be 12 over 3, that'd be 4. The answer is 4,000. 4,000 people. Don't just put 4, it's 4,000. What's the population in 6 years? Plug in 6, 5.2. Again, don't put 5.2, it's 5,200 people. The limit, plug in infinity. Well, when you plug in infinity, what do you get? You get 11 infinities plus 12 over 2 infinities plus 3, which is an indeterminate form. So when we have an indeterminate form like this or like this, we have more work to do. And the simple work is, hey, it's a polynomial, just look at the front, cross those off, 5.5, and now it's not a value, it is a limit. These don't have values, but they do have limits. Alright, so when is the population going to reach 6,000? Well, never, right? If the population has a limit here, well, it can't reach 6,000. It's just a comprehension question. 13, horizontal asymptotes are, when we have that definition, we test this, we test this. When you see this, you have 2 tests to run. And these are the tests. Test this and this. Plug this in here. I have a negative infinity, which makes it a fraction. Well, 1 over a large number is 0, 5 halves. Over here, plug in negative infinity. Well, negative makes it a positive. Well, that's infinity. 5 over infinity is 0. Those are your 2 asymptotes. Because we have numbers here. If we have numbers, we have asymptotes. If we have infinity, we have nothing. Let's just graph this, see if we can get a picture of this. 5 divided by 2 minus e to the negative x. Close that parentheses, close the denominator, zoom standard, and there's our asymptotes. Horizontally right here, let me go ahead and change that window. We only need to go up to 2.5, so let's go up to 4. We only need to go down to 0, so let's go down to negative 2. Well, I'm going to go down to, let's go out to 10, and let's go down to negative 2 and go up to 5. Take a look at that graph right there. That graph right there, if I hit trace, look what those numbers are getting close to right there. If I go to the right, where is it going down to? 2.5. And if I trace over here, I didn't go out far enough. Let's go out to 10. If I go here, if you can barely see that graph right there, let me not go up so high. If I only go up to 2, there's that graph. If I'm going to the left, you see it's going up there and it's going closer and closer and closer to 0. Let's really zoom in on that. Let's go window. Let's go only to 0.1 high, and let's go down to 1. Take a look at that graph there. It goes up and it's getting closer to that number right there. Alright, 0. And those are asymptotes. Horizontal, side to side. There's a line here at 2.5. There's a line there at 0. And last page, find a limit. As x goes to negative infinity. Plug in negative infinity. Again, just the powers, the highest powers. Divide here, I have this. Plug in negative infinity. And you got to be careful here. This is negative infinity squared, which would be positive infinity. That's infinity. That's unbounded. The graph will go up like, whoops, we're going to negative infinity. So this is what I know about this graph. On the negative infinity side, it goes up forever. You can just graph that, right? Let's graph this version of it. Windows, 2x squared divided by 5, zoom standard, and there's the negative infinity side. Negative infinity side, it's going up to infinity. Well, on the positive side, it's going up to infinity too. And if you graph this, you get the same end behavior. Discontinuities are when we divide by 0 -7, -2. The types, the -7 is removable. The 2 is not removable. It's infinite. Asymptote, whole, removable. These go together. Limit here, plug in infinity. Again, cross them off. 3/5. What does that mean? It means there's an asymptote there, right? If I go ahead and graph this, y is equal to 3x divided by 5x minus 1. Assume standard. Yeah, there's that value right there. It's a little bit too high. Let's not go up so high. Let's go to -2, +2. There's that value right there. Where is it going? Hit trace. I bet it's going to that. Look at those numbers. 6,5, scoot over a little bit. 6,3, scoot over a little bit. 6,2, scoot over. It's going to 0.6, 0.6. And if you go out to infinity, it would be there. Horizontal asymptotes. Test, test. Divide, divide. Same thing. There's only one. Describe the end behavior. The end behavior means it's like the horizontal asymptote test, except we're not going to use the words does not exist. We're going to say, look, this is going to infinity. As x goes to infinity, f of x goes to infinity. And as x goes to negative infinity, this goes to 0. Now, if we were doing horizontal asymptotes, this is a horizontal asymptote. That's unbounded. But end behavior just means give the results. Don't interpret it. Number 4. Plug it in, do the math, you get 3. Vertical asymptotes, factor it. My options are this one and this one, -1, -3, not removable. So it is an asymptote. This is removable, it's a whole. And the question says vertical asymptotes, so that's my only one. And some limit practice. Well, multiply by both of these, simplify, plug in, you're down to here. Some trig identities. Can't plug this in, but you can change this into that. Probably the most important trig identity is sine x, or sine squared, plus cosine squared x equals 1. This trig identity will lead you to that one. If you just subtract that over there, take out cosine, and now this is a squared plus b squared equals, or a squared minus b squared. A plus b, a minus b, cross those off. Now you can substitute them in. Alright, that's everything you need to know for the test. Hope this helped. If you have questions, I will see you in class.